Hi everyone, today I'm going to explain how to apply the principal component analysis by using Stata. But before going to the software, I want to clarify some aspects about this method. So let's go to a little presentation that I prepared. So we use the principal component analysis when our objective is to reduce the number of variables from a dataset through a linear combination between those variables. And after that, we are going to obtain new uncorrelated variables. And those new variables, we are going to call them components. In other words, we use PCA when we seek to reduce the number of variables from a dataset when we know there are correlated variables within. How to use it? The first step is to choose the most relevant variables and also to be sure that those variables are correlated. After that, we use PCA method, and as a result, we will determine the linear combinations or components that we are going to use because they captures the largest amount of information. It is important that you keep in mind that our principal objective is to not lose information from the original data. Therefore, the PCA must explain the same variability of the original variables, but using a less amount of variables. This is because the idea is always to have the greatest amount of information, but the fewest amount of variables. Because when you have a large amount of variable, therefore your analysis will be more complex to develop. Also, some aspects that you must not forget are that the components are linear combination of the variables, and therefore they are not correlated. This is because it is expected that each component represent different information, different variables. Also, the most relevant components are those that captures, as I say, the largest amount of the total variance of the data. And finally, PCA creates as many components as variables. So for example, if I want to apply the principal component analysis by using 5 variables, Stata will present me 5 components, but after that, I will decide how many components I use at the end. Some assumptions about this method. The first one is that the first component, or component number 1, must have the largest amount of information, and so on. Also, when the coefficients of each components are added and squared, they must be equal to 1. Remember that when we talk about the coefficients from the components, we are talking about the eigenvectors. And finally, as I said before, the component values are not correlated. So I think that we can start using Stata. For this video, I'm going to use again the dataset encuesta. So remember that we use the command use and the name of the dataset. And for this first part of the analysis, I'm going to use only 2 variables, which are going to be estatura and peso, which represents the height and the weight of the respondents. So first, we could, for example, use the command summarize. You also can write only sum as an abbreviation of the comment summarize. It will present the same information. And we're going to choose the height and the weight. And here, well, just as I show you in the last video, we can analyze the number of observation from both variables, the mean, the standard deviation, and the minimum and maximum values that those variables assumes. Also, remember that if we are going to apply the PCA, we want to validate if those variables are correlated. So we can use the command correlate or just core. And again, the same two variables. And here we can observe that those variables are related in a positive way. This is because the correlation between both variables are higher than 0.7, and also it has a positive sign. This means that a higher height represents a higher weight in a respondent. Maybe this is more easily to understand by seeing a graph. So for example, if we can like build a graph by using the command scatter and the two variables that we want to use. And here, Stata will present this graph in which you can observe how higher weight represent higher height. Also, for example, we create like graphs divided by some categories that we choose from the variables. So for example, I want to graph the height and the weight, but divided by the gender of the respondent. So to do that, we will use the command two-way scatter, the two variables that we want to graph. And for example, I want to see how the height and weight behaves according with the gender of the respondent. So I'm going to write a comma by open a parenthesis, and after that I'm going to write the variable género, which represents the gender of the respondents. So Stata will present a graph in which I will see the relation between the weight and the height, but categorized by the gender of the respondents. Here, for example, we can assume that the man has a higher weight and height than women, but the relation between those variables, it's the same for both of them. Weight and height has a positive correlation in both cases. Now we can apply the principal component analysis by using the command PCA and the name of the variables. So here is like the output that Stata presents after using the principal component analysis. Here we will have the number of observations and also the number of components. Remember that I told you that Stata will create the same amount. Stata will create an amount of components that is equal to the variables that you are using. So here I use estatura and peso. So Stata is creating two components. trace refers to the variability of the data. So in this case, the total variability is 2. And here, well, we will find the information about the 2 components. Maybe we could like go back to the assumptions. And here, for example, we have said that the first component have the largest amount of information. So that could be proved by analyzing this column, which name is proportion, because this, for example, this number shows the proportion of the variability that the first component represents from the data. So we can assume that the first component captures the 86% of the total variance from those 2 variables, and the second component represents a lower percentage of variance. Also, when the coefficients of each component are either n squared, it must be equal to 1. Remember that this is when we talk about the coefficients, we're talking about the eigenvectors. So I write the eigenvector of each component in Excel, and let's just add it and power the eigenvectors for each component, and it must be equal to 1. So first, I'm just power, and I'm going to add it. And here you can see that it is 1, and it is going to be the same for the second component. Please do not get confused with eigenvectors and eigenvalue are different. And finally, components values are not correlated. To prove that our components are not correlated, we will first need to create the components as variables. So to do that, we are going to use the command predict. And after that, we are going to assign names for each of the components. So for example, I'm going to just assign comp1 to the first component and comp2 to the second one. And here, Stata will create a variable for the scores for component 1 and component 2. And with those variables, we are going to calculate their correlation with the same code command that we used before. And here we can see that they are not correlated because they represent different information. Also, for example, we can create a graph with both components. And here you will see that there is not like, it is not possible to determine if there is a correlation, because there is no, like the points are not following a pattern. So we can assume that there is no correlation by using only this graph, for example. But by seeing that the correlation is equal to 0, we can argue that there is no any correlation at all. Also, for example, we can try like to calculate the correlation between the variables that we use in the principal component analysis and, for example, one of the components. So, sorry, I'm going to use estatura, peso, and component number 1. And here you will see that component number 1 is even had a strong correlation. Component number 1 has a strong correlation with the height, but also with the weight of the respondents. And this also could be seen by using a graph. To do that, because we are going to grab 3 variables, we are going to use the command graph matrix. So we're going to grab estatura, peso, and component number 1 again. And you must keep in mind that this information, which is present here, is the same as is that is present here. So maybe to have a better graph, you could write a comma and after that half. So Stata just only present the information also. And here, well, we can see again, like in a graphic way, how is the first component correlated with the weight and with the height of the respondents. Now, maybe we could try to use the principal component analysis with more variables. So let's start again. So I'm going to use again the dataset encuesta, and the PCA I'm going to apply to estatura, peso, and all the variables that are related with grades, which are this one. Okay. So here we are using 7 variables. So Stata is creating 7 components. Now I want to talk more about the Asian values. These Asian values represents the variance of the principal components that is represented by the covariance matrix of the X variables. The Asian values, when you sum all of them, must be equal to the total variance. This is the trans that I showed you before. And also, people usually only consider the components which their eigenvalue is greater than 1 or close to 1. And finally, about the eigenvectors, as I told you, those are the coefficients for each of the components. And also, Stata will present the eigenvectors, but also an unexplained, which is the variability that it's not explained by the model. So let's go back to Stata. So here we can see that as before, the first component has the largest proportion of variance from the data. And also we can see here that there are only 2 components that has an eigenvalue which is higher than 1. So we can, for example, assume that we are only going to work with the first 2 components. And here Stata presents the eigenvectors for each component and their the variables. So here, for example, if we analyze the eigenvectors, we could assume that, for example, the first component represents mostly the information about the grades, the variables that are related with grades. while because this is because the eigenvectors for this component are not only positive, but higher than those eigenvectors from the height and weight of the respondents. Nevertheless, in the second component, we have that the eigenvector is higher for the height and weight, but no for the variables related with the grades. So while this component is represent the variables related with grades, this component is representing the information about the height and the weight of the respondents. For example, we can also create a script plot. So a script plot is the graphic representation of the eigenvalues after we use PCA. So remember that the idea is to only use the component which eigenvalue is higher than 1. Maybe like to make this more clear, we can add to this script plot a line in the y yes, like a line in 1, so we will identify easily which are the components that have an eigenvalue higher than 1. And finally, we can add to this graph, you will write Ci and parentheses, and this shade that you see here is like an interval, a confidence interval of 95%. So with a confidence of 95%, I could assume that the first eigenvalue for the first component will be between this point and this point. For the second one will be this one and this one. So maybe this is helpful when you are going to decide to use or not a component that which eigenvalue is close to 1, because maybe the confidence interval will maybe be higher than than 1, even if the point is not higher than 1. But in this case, the interval is not higher than 1, so we are not going to use it. Now I'm going to create the 2 components that we are going to use by using again the command predict, but this time I'm going to call them C1 and C2. And here Stata will present again like the eigenvectors, and also we can, for example, create a loading plot for the first 2 components. Sorry, plot. Good. So in this graph, we could see that for component 1, the loading plots are strongly concentrated here because this component represents the variables related with grades. So the loading plots for those variables are positive, while for those 2 variables are negative in the case of component 1. But in the case of component 2, even if all the loading plots are positive, those that are higher than the rest of variables are height and weight. So as I told you, this component represents variables related with grades, and the component two with, for example, we could say with the health of of the of the respondent, with the height and weight. And yes, I think that's all I have to present you. Do not forget to always keep in mind the difference between the eigenvalue and the eigenvectors. They could sound similar, but represents different information. Just to finish, for example, here we use the first two components, so we are in total we are using the half of the variability of the total data from the original data, because those two components together uh, represents the 55% of the variability. So it's something that you may keep in mind. So well, I hope you'll find this video useful. So see you next time.